There are various properties, first of all, that transmission lines have. So remember, a transmission line is an electrical conductor like any other. Yeah. If it is a 3-wire conductor, it is a set of 3 circuits. Remember what we said about 3-phase power. Generally, they are 3 circuits separated by 120 degrees from each other, but they have certain relationships between each other. So if you have a transmission line, if you have 3 sets of wires traveling long distances, hundreds of meters, maybe even hundreds of kilometers, long distances next to each other, there are bound to be certain effects of those wires. The first, of course, is resistance. Because these are real-world wires that are made of copper or aluminum, definitely they will have a resistance. And because that resistance is a property of the length, just like the weight, the resistance increases with the length. Number 2 is the inductance. Now, this particular one, when you have a cable that carries current, anytime you have a current flowing through a conductor, what will happen? You will have a magnetic flux being set up around the conductor. So the inductance is because of the flux set up, or it is the interaction of the conductor material with the flux set up when AC flows through. Remember what we talked about, I think it was Faraday's law, that anytime there's a change in a current, and remember AC is a constant change in the magnitude of the current. It is constantly increasing and decreasing and going negative and coming back to 0 and so on, several times per second, 50 times per second. So that particular interaction means that there is always an inductance effect within the cable as long as it is carrying current. The third property is capacitance. As we've said, once you have long conductors that are operating next to each other, they are positioned next to each other and they are carrying currents next to each other, they have voltages set up. Anytime you have conductors separated by insulation, what do they form? They form a capacitor. That is essentially what a capacitor is. A capacitor is 2 conducting plates separated by a dielectric, or in this case, the insulation. And transmission lines are the same. The insulation that is there between them, if it's an underground cable, will be an insulating material. The insulation for an overhead cable would be the air itself. So with this particular property of transmission lines, it really comes into effect at high voltages and high distances. The effect of capacitance over short distances is very low. So that brings us to classification of transmission lines. So we have 3 types. We have what we call short transmission lines, which are less than 50 kilometers and also less than 20 kV. So as we said, the voltages are what determine the classification of the transmission line. These transmission lines will tend not to have much capacitance in them, short transmission lines. Medium transmission lines, we have 50 to 100 kilometers and 20 to 100 kilovolts. And finally, we have long lines, which are greater than 100 kilometers and with voltages of more than 100 kV. Long distance and high voltage. Another aspect of the transmission lines is called voltage regulation. Now, voltage regulation is the effect of applying a load to an electrical circuit. So we say the percentage of voltage regulation is given by Vs minus Vr over Vr, where Vs is sending end voltage, which is voltage at the source, and then Vr is receiving end voltage. That is generally the voltage at the load. So at the consumer's position or at the transformer in terms of a substation, wherever the destination of your transmission line is. So this measures how much drop in voltage you experience by passing voltage or passing power through a specific transmission line. So it will depend on many things. If you have a long distance cable, for example, The impedance that you will get due to resistance, inductance, and capacitance has an effect. The inductance and capacitance of the transmission line will change the power factor. So the voltage at the sending end will be different from the voltage of the receiving end. They might even be out of phase. So let's look at what the characteristics of the transmission line look like. So in a simplified version of the transmission line, if you would imagine your circuit to look like this, because all electrical circuits, whether they look like 3 lines or 4 lines or however many lines, generally you will have a source, which is here, you'll have an impedance, and you'll have your load, whatever the load may be. Now, for purposes of our discussions, as I've said here, we'll be looking at short transmission lines. And in the case of short transmission lines, as I mentioned, the effects of capacitance are quite low to the point of being negligible. So in our discussion here, let's look at lines as being short, and we see how we can describe them. So now what you will have here is you have at the point of receiving, you have your current I. The same current flows all the way through the circuit. However, you have a voltage at the sending end. You have a certain voltage drop due to the transmission line itself. We are counting this section to be the transmission line. And in case I didn't mention it before, when I say transmission line, I mean lines that are both in the transmission section and also distribution. Any line that carries power over a distance. So this is your transmission line. So your transmission line will have the effect of dropping some voltage. It will have an impact on the circuit. Even though you have a voltage drop, remember that the current itself remains the same. It will still supply the load. It will flow through the source, the transmission line, to the load. What changes is your voltage. Remember, we are looking at voltage regulation. What is the difference between what you send from your source and what you receive at your load? So let's look at that. Let's look at the phasor diagram of what you have. First of all, we take the voltage at the receiving end as your baseline. Let's talk of VR. That's your receiving end voltage. It has a certain magnitude, and since it is our reference point, we will say that it is the angle, the base angle. Let's say it is at 0 degrees. A certain magnitude V with a phase angle of 0 degrees. The current I, let's assume a lagging current. So remember, we said a lagging current will be in a phase behind the voltage. So the lagging current in this case has a phase angle of phi r, yeah, receiving end. The phase angle at the receiving end looks like that, yeah. The difference between the angle of the current and the angle of the voltage. Voltage at receiving end is our reference. It is taken to be 0. So this is the condition at the receiving end. Let's look at now what the conditions are due to the resistance and the inductance. Now, if you have your resistance itself, the voltage drop due to the resistance will be given by IR, and IR, a resistance, does not change the phase angle of your current. So it would be in parallel, same angle, in parallel with your current itself, okay? Resistance does not change the phase angle. It has a 0 phase angle. If we take your current I, it is at that angle, the inductance itself will turn the current, or it will change the phase angle of the current by 90 degrees, such that the resulting voltage drop, Ix, that voltage drop will be at 90 degrees to the current itself, right? Current is assumed to be in that direction. Remember, these are all parallel to each other, okay? Here is your current. And the impedance due to the inductance changes it by 90 degrees that direction, yeah? The angle between the two is 90 degrees. So what do we have at the sending end? Now, if you look at this circuit and if you take the total voltage all around, the voltage that is supplied at the source is equal to the voltage drops, which are here, it drops here, it drops here, plus the voltage that is supplied to the road, or the receiving end voltage, all right? So this Vs is the sum total of all the voltages within the circuit. Now, if we look at it from the vector point of view, the vectors will therefore be found by adding, or rather the vector value of Vs will be found, if this is a vector and this is a vector and this is a vector, it will be found by adding up all those vectors. So IR is a vector, IX is a vector, and VR is a vector because it has a magnitude and a direction. The direction in this case is the phase angle. So in order for us to identify Vs, we need to add up all the vectors. And we've already drawn all the vectors here. Those are the ones that we have indicated here. We said that the voltage drop due to the resistance is parallel to the voltage or the current that we have here. Yeah, they're in the same phase angle. So we add it to what we already have. Likewise, Ix is added to that, right? That is how, see, that is vector addition. That is the addition of all the vectors one after the other, so that you end up with the sum total of those will give you the vector value at the sending end. So Vs will be there and it has an angle alpha at that point. So what we've ended up with here is the vector diagram or the phasor diagram of your circuit. The transmission line with all its voltage drops and its load has a vector diagram that looks like that. So now once we have this vector diagram, we can look at certain aspects of the vector diagram. You note that, of course, this is 90 degrees. You can create an equivalent voltage drop, which is the sum of the resistance and the inductance, and we can call this IZ, where Z is the sum of the resistance and the inductance, the impedance due to the inductance here. Z is the sum total of these two, the vector sum of these two, right? So what that would mean is our Vs, our sending end voltage, is equal to VR, receiving end voltage, plus IZ, which is in turn equal to VR plus I times R plus J. So you can see from here, the transmission lines have an impact. And let's see some of that impact in terms of an example. So you have a single overhead transmission line which delivers that much power at 33 kV at 0.8 power factor lagging. So you have your voltage at the sending end. It passes through your transmission line. Let's call that ZTL, which is R plus JX. And it supplies a load and it returns it back. Okay, so Vs is here. Our VR is at that point. Okay, and this is our representation of the components of your transmission line. Okay, so we know at this point it is delivering 1100 kilowatts and the VR is equal to 33 kV. Okay, this is a single phase overhead transmission line, right? We are also given the total resistance and inductive reactance of the line are 10 and 15 respectively. So to be clear, let's remove the Z and we actually show the components that we have. So we have from sending end, you have your resistance of the line and you have your inductance of the line. So the resistance equals 10 ohms and the inductance equals 15 ohms, or the impedance due to the inductance is 15 ohms, right? And we know the load is at 0.8 power factor. Okay, so we want number one, sending end voltage. So we are looking for what is the value of sending end voltage. So luckily we know everything about the voltage at this point. We know the angle, we know the amount of power, and we know the VR. Because we know all this, we can find the current, which is the missing component. Because we know the power, we know the current. So we have Z equals R plus JX due to the transmission line, which is 10 plus J 15. That's item number one. And we also know that at the receiving end, the power factor is 0.8, which is equal to cos phi. Therefore, phi is equal to cos inverse of 0.8. Let's bring out the calculator. So what is the inverse cos of 0.8? Which is 36.87 roughly. Okay. So now from all that, we can find the current. So how do we find the current? We know power in this case is given by that. This is a single phase circuit. Power is given by that. So if we rearrange, we get current is equals to P over V cos phi. Okay. So what is our current in this case? Current is equals to 1100 kilowatts, so it's times 10 to the power 3, over voltage, it is 33 kilovolts, so it's times 1000, times cos phi, which is 0.8, which is there. So 1100 times 10 to the power 3 divided by 3300 or 33,000 times 0.8. So that gives us 41.7 amps. However, remember our phasor diagram here, right? The voltage at the receiving end is at 0, but your current has a phase angle phi, which is what we have calculated here. Okay? So in this particular case, your angle, your power angle, or rather your phase angle, will be included in your answer. So it is not just 41.7 amps, it is 41.7 amps at an angle of negative 36.87 degrees. Okay, we have to take into consideration that power factor, otherwise it won't add up. So now that answer, let's now include it in our, so it is that. So I can also be expressed as 33.33 minus J25 amps. All right. If we were to draw the phasor diagram of the circuit that we have so far, it would be, that is our voltage, that is our current. So our current is 41.7 amps at an angle of 36.87, okay, degrees. And then you have now your IR, which is here, and your IX, which is there. IR, JIX, which will in turn add up to, IZ. This is VR. And then that will give us what we are looking for, which is our sending end VS. Okay, so that's our phasor diagram of our circuit. Now, what next do we need? We need to find VS, and we have the phasor diagram that looks like that. So we said that VS is equal to all of this, is equal to VS, is equal to VR plus I times all of that. So now VS is equal to VR, which we know, plus I, which we also know, times R plus JX, which we also know. So we can get all of those because we know all of them. So VR was 33,000 volts, and we've said that that one is at an angle of 0. So that one is fine, 0 degrees. Plus, so now we have our current. Our current is given as this, okay? So the current is 33.33 minus J25 times our two values of impedance, which were 10 and 15, which are here. So 10 plus J15. So we can evaluate this straight away in the calculator. So this 33 minus J25 is already on the calculator here. So let's evaluate that. Times we want to do 10 plus 15i. So that gives us our answer. So it is 33,000. Because it is at 0, we can disregard any complex property, plus 708.33 plus J 249.99. Adding all those up together, let's add 33,000. You get VS is equal to 33,708.3 plus J 249.999 volts. Okay, so that's our sending end, right? From the calculator, we can directly convert it from this rectangular into polar. So we can find straight away what is the angle that we have here. So in this case, our sending end voltage VS is here, right? If we want to represent what this means, what the answer we've gotten means, we draw a line from there and a line from there. Yeah, so for the VS only, this component, roughly 250, is the complex one. So it is J250. It is the vertical one there. And then this component, 33,708, is the total that you have all the way along here up to there, right? So that is 33,708, okay? And when you square both of those, you get VS, yeah? So what is VS? The magnitude of VS with the angle of alpha. So you can convert that in your calculator into polar, and it is given by that. So it is 33,709 at an angle of 0.42, let's call it 5. So that alpha is 0.425 degrees. Okay. So our sending end voltage is represented in polar coordinates 4.26 at an angle of 0.4249. Notice that it is leading the receiving end. It is up, it is above. Anything below is lagging. Anything above our reference is leading. Okay. So now the final thing that we need to do is, what is the sending end power factor? So sending end power factor is here. So the sending end power factor is simply cos phi r, whereby phi r in this case is given by that. Okay. So the power factor that you have there would be is equal to cos. So the total of these, you have 36.87 and you have 0.425. So the total of those, 36.87 plus 0.425. The total of those, 36.87 plus 0.425. So our power factor will be 0.795. Now from there, we actually then we are looking for the efficiency. So the efficiency in this case is given by output over input, and it is given in terms of powers, right? Now, how do we get the power? So remember we said that our power at the output is 1100 kilowatts. Okay, efficiency is always a component of it's always comprised of power. It's a function of power. Input equals 1100 kilowatts. Output. But what is the input? The input is equal to output plus whatever losses we encountered in our transmission line. Okay. Remember, we are talking in terms of real power, right? Actual losses. Efficiency is about work, the amount of work that is done. And last time we said that the amount of work that is done is a factor of power. So our output, which is known, which is 1100 kilowatts, will be added to the losses. Losses are I squared R. Okay. So in this case, R is our transmission line. We do not include the impedance or the inductance. We are only including real power. Okay. So in this case, it will be 1100 kilowatts plus 41.7 squared times 10. So input equals 1100 times 10 to power 3, because they are kilowatts, plus 41.7 squared times 10. Okay, so that gives us 1,100,000 and so on and so forth. So 1,117 point, let's call it 39 kilowatts. So our efficiency is equals to our output, which is 1100 over 1117.39. And that gives us 98.44% efficiency. So the last thing we are going to cover to do with transmission lines is corona effect. Here we are talking about a certain effect that is found on very high voltage lines. It's usually most prominent on extremely high voltage lines. But the insulator that separates the cables from each other is air in overhead lines. And air has its own dielectric or insulating properties, just like any other insulator. So at a certain voltage, those insulating properties can fail. If you have conductors, let's say if this is one conductor and that is one conductor, and they are carrying current within them, the insulating properties within the dielectric that is in between them can tend to break down due to various properties. The distance between the two conductors is one factor, and also the voltage between the two is another factor. And at the same time, now the dielectric properties, which are the properties of the insulating material, or in this case, the air, right? So the corona effect is the effect that you will see once the voltages are so high that the air surrounding the conductors now starts to break down and conduct. This will take the form of ionization. So you will tend to see ionization of the air around the conductors, depending on the shape and the distance and so on, the properties of those conductors at those very high voltages. Okay, and ionization of air takes the form of a sound. It can be like a hissing sound, almost like a buzzing. And in some cases, it can even produce light. And that is where the word corona comes from. It looks like a glow that is surrounding the conductors that are there. So when we are analyzing this effect, we talk of a critical disruptive voltage. So this is the voltage beyond which the air breaks down, the voltage breakdown. We've said the characteristics of this is a glow, usually violet. It has a hissing sound or a buzzing sound, and it also produces ozone. And ozone, of course, is a compound of oxygen, which has a distinctive smell. So you would even be able to smell that particular gas in an area where you are having the corona effect. And the effects of corona is not just, a disturbance due to the glow itself. It can actually cause corrosion. Because the air breaks down or oxygen forms ozone, that ozone can cause corrosion of the electrical components. So it is important to understand the effects and take the effects into account. So this critical disruptive voltage, we said it is determined by various factors. So we will list them here: M0, G0, delta, R, natural log of D over R. So these ones, MO represents the irregularity factor. So the corona effect is reduced in components that are, or rather the voltage itself is reduced in components that are more irregular. So in cables that are very shiny, yeah, the corona effect is less. That voltage is lowered, yeah, the critical voltage is lower. So the shinier it is, the higher it is, the more irregular, the more spikes and so on you have, it brings the voltage where corona can happen to a lower level. G represents the dielectric strength of the air, and this is affected by various properties, humidity, the amount of dust and so on within the air, various characteristics of the air, how, the altitude and so on and so forth. All those have an impact. Air density also has an effect, and R is the radius of conductors. And finally, D, which is what we saw before, the distance between the conductors. So all these factors are the ones that determine at what voltage the air will now start to break down. So we can look at an example of very simple example. If you have a high voltage line, remember this usually occurs in high voltage. So if you have your 240 or even 415 or even 11 kV lines, you will not see this effect. Yeah, however close they are, the voltage is not high enough to break down the dielectric properties of air. This is seen at very high voltages. So you have your line with conductors that are at this diameter, fairly small conductors. And it is built so that corona takes place if the line exceeds 210 kV, right? RMS. The dielectric strength is that. Find the spacing between the conductors, assuming that factor is 1 and that other factor is 1. So that allows us to really disregard the effects of those. So we've been given the diameter. Let's get our radius. Bring the capacitor, not the capacitor, the calculator. Bring the calculator back. 1.956 over 2. 1.956 divided by 2. Sorry, 1.956. It is 0.978 centimeters. Okay. Disruptive voltage is 210 kV. Let's put it in terms of per phase, which gives us 210 divided by root 3. It is 121.24 kV. And then now we have, so we now want to have our VC. So VC is equal to M0 G0 delta R ln D over R. So we know VC, 121.24 kV, is equal to M0, we've been told to assume 1. G0 is 21.2 kV. Delta as a density, we've assumed 1 times radius, we've been given 0.978 times ln over D. D is what we are looking for, over R. Okay, so let's rearrange a bit. Ln D over R is equal to 121.24 over 21.2 times 0.978. Okay, we can keep the distances in centimeters so that we retain our units. 21.2. The kVs cancel out, so we can retain those units as well, 0.978. So that natural log is given by 5.8475. Okay. Now, in order for us to get the natural, to resolve this, we can raise both to the power of E. So D over R is equal to E to power 5.8475. and we rearrange again because we're looking for D. D equals E 5.8475 times R. R was, question? 0.978. So E to power 5.8475, sorry, 5.8475 times 0.978. It will give us that. So the distance between the two conductors is, sorry, 338.7 centimeters. So that's roughly 3.387 meters. Okay. So if you want to prevent corona taking place, you must distance your cables more than 3 meters apart. That's fairly large, and this partly explains why you would need to have, in terms of high voltages at 132, you usually see them being huge pylons with huge distances. 3 meters is fairly large, yeah, and that's a big distance to be separating your cables from each other.